postulate or propose a solution. Yeah, we call this is sometimes postulate. Okay, the postulation. This means this looks a bit different, but it's more like a guess. Okay, this is more guess what is the proper solution. Okay, it's more like a make guess. Let's say make an educated guess. For the structure of the solution. Okay, so for example, right, what I mean by this is if you have a fluid and then this fluid is driven by the wall, right? I mean for create flow. When you have a create flow, you would never expect there is some flow going upward, right, or going downward. It is impossible. Right, so this kind of things, we want to make some kind of reasonable guess. Try to eliminate the extra variables. Yeah, that is one part. For the second part, that's part one. The second part is the check the proposed solution with the continuity equation. Okay. So the idea here is the continuity equation is also a equation that must be satisfied always. Okay. This is a mass conservation, right? So for whatever the cases, right, you must have the continuity equation always satisfied. So you are proposing some solution, and then this is more like a sanity check. If your proposed solution doesn't even meet doesn't satisfy the continuity equation, there is no point of examining further. Just make sure your solution is they still agree with the continuity equation. This is the second thing you want to do. Third thing is the simplify the Navier-Stokes equation. Yeah, sure. Okay, so yeah, that's exactly the point here. So in this case, right, this is a Navier-Stokes equation. There are so many terms, right? But for example, if your solution is guessing u equal to 0, then the u equal to 0, then this, right? All of this u term is going to be 0. Also, this entire u is 0, right? The viscous term is going to be 0. So now you can simplify the entire structure of the equation a lot easier. Okay. Using the proposed solution. Okay. Number 4 is the let's say identify the boundary condition. This is something identify the boundary conditions. Wait, this one is the okay. Boundary condition, and this is the based on the physical condition. For example, the location of the wall, location of the moving surface, location of the interface. You can probably get some information for that. That is the number 4. And then lastly is the solve the differential equation. Okay, so that is more like a 5 key steps. Okay, So let's try to do this. Do you have any questions for this step? And then I mean my intention here is let's try to do these steps using this the specific condition, the correct flow, and then other flows. Okay. So okay, this is just a quick draw of the viscosity here. This is the so let's say the flow is, let's say go A is create flow. This one is the idea is you have some wall, and then this wall is moving at the speed of u, and then we do have a stationary surface here. Okay? And then right now, okay, we are not making any assumption. Okay, we last time we said okay, this is going to create a linear velocity profile, but there is no evidence for that. So at this point we don't know how those the flow look like. So instead let's say let's say in this case this direction, this direction is the x, and then this direction is y, and then we can also say this direction is z. Okay, this is a create flow that we should have here. Okay, and then by the way, the viscosity is going to create a shear stress. So this is going to be it's going to be okay. Let's say shear stress is the tau, and then viscosity is mu, which is typically this is going to be described by the du dy in this kind of particular cases, but it's also specific direction specific. Right. So we are now considering something called the create flow. Okay, so create flow is the another name is a shear driven flow. Is the to have two parallel plates, and then this also describes the cases, right? For example, the one type of the shear driven flow in this case is the you have a bottom plate which is stationary, and then top surface is the moving. Okay, that is one of the example. Alternatively, you can also consider, for example, you have some slope in this slide in the picture, right? You have some block, and then this block is moving. This block is sliding down. Maybe I can draw. Other example is I think if you remember some of the case problem. You have some slope, and then you can have some object, right? And then there is some fluid layer in between, right? And then okay, so the object sliding down. This is yet another example of the create flow. If you really carefully examine the velocity profile, this one probably is looking like something like this, right? So in any case, though, this particular example of the moving wall is the one of the easiest example here. Right. So let's try to solve this. Okay, by following the steps that we specified here. So the first step is the postulate or propose a solution. Okay. In this case, if you ever have this kind of the flow, what do you expect the flow look like? This one, we need a bit of thinking here. In this case, okay, we are probably, when you postulate, right, we are looking at the U, typically U, B, W, which is a three component, right? With this, cases, right? Okay, you have a plate on the top, you are dragging. Okay, you have a plate on the top, you are dragging this plate to the right. In this case, do you expect there are any flow in the z direction? No, right? I mean, this one is good. Okay, you can agree. In the z, there is no flow coming out of the plane or coming inside of the plane. Okay, so this one is supposed to be 0. And then alternatively, do you expect there are any flow in the going up or down? Probably not, right? I mean, this is, if that is allowed, then, some materials accumulate in the top, some, or, there's more fluid accumulate in the top, and this is going to contradict. Most likely, there is no vertical flow. Okay, this is no flow out of plane. Okay, that is W. And then, so the only velocity, only velocity or only speed that you may expect is the U, which is in the direction which is aligned with the motion of this fluid. Motion of this, the wall. Yeah. Yes. Yep. Sorry. Yeah. So in this case, okay, we also make one other additional idea. If you consider you can potentially, right, depends on the 4 variables. You can depend on 4 variables. Okay, so this is you start. Okay, we start from the u can be potentially u of the x, y, z, and t. Okay, this is the potentially those are the 4 variables that can define the that can describe the u. Okay, so in this case, right, what is the valid variable? Let me go with something easier, right? Okay, do you expect u should depends on the z, which is the the different location in the plane? Probably not. Or do you probably not, right? So it's probably it should not depend on z. Do you expect you should depends on the time after in this case you are going to pull this, right? And then for this wall is infinitely long wall, so eventually they're going to achieve the steady state, right? That is the assumption. So it should also not depends on the t, right? So this is eventually steady. Okay. Last 2 things is does u depends on x or does u depends on y. So the x is the at the different location along the floor. And the y is at the different distance between the wall.
I don't think it depends on x, but it depends.
Okay, the one of the opinion here is it should depends on y but not with x.
Since as long as the whole thing is uniform across the whole.
Yeah.
Yeah,
that's actually a good observation. Do you get this argument? Okay, so the argument here is let's say the consideration you want to have here is the following. Okay. Okay, so let's say this one is moving at the speed of u, right? Okay, so now the comparison you want to make here is for example, okay, this guy. Let's compare these two fluids. Do you expect these two fluids can have a different speed or can be the same speed? It should be same, right? I mean, if this is going to be different, again, there is some point, there is more fluid coming. Whatever comes in, whatever should comes out, right? Whatever coming in, whatever should come out along the same plane. So for these two should be the same, okay? So if I set here, right? Okay, so This is the, if I write it in the coordinates, this one is a x1, this one is a x2, right? So the argument here is basically telling the u doesn't depend on the x. U should not depend on x, okay? Does not depend on x along the flow, okay? How about the, if you want to compare these two different heights, for example, in this case, let's say this is the y1, y2. You want to compare these two fluid particles, right? I don't know how it varies, but the one is closer to the wall, the other one is closer to the stationary wall. One is closer to the moving wall, the other one is closer to the stationary wall, right? So do you expect they are different, right? So in fact, you know, this might be the case. We don't know how they vary. U depends on U depends on y, which means, you know, how close to the wall. Okay, so this is going to tell you, okay, now, you know, by the simple argument, okay, u shouldn't depend on z, right? And then you shouldn't also depend on t, because eventually it becomes stable, steady. And then this also argument tells u does not depend on x, but u is going to depend on y, right? So this is my guess, right? I mean, I don't know, I mean, but at this point I'm only making a guess. But the only variable with regards to u is the y. That is the assumption we are making. This is like, you know, what we mean by the postulate. So u should be u of the y only.
Bro,
Yes?
can you explain again why it's not dependent on the x? U is the speed of the moving object, right?
Right.
How come it doesn't depend on the x again?
Do you think, you know, along the same plane, the fluid is going to accelerate?
That means we're assuming it's a uniform flow throughout.
I mean, we're not making assumption. But this is what do you expect, right? I mean, so at this point, you know, we are making a guess. But do you think my question is if you are pulling this guy, right, at the same speed, you are pulling this u at the same speed, and then once they establish the sort of steady state, right, do you expect the fluid flowing at this location is flowing at a different speed than this fluid? It should be the same, right? So then, you know, this is saying, you know, depending on a different location at x, the fluid particle is moving at the same speed. Alternatively, if you look at the particle, right, I mean, this depends on how close to the moving wall as well as the stationary wall. And then my guess is if the fluid particle is closer to the stationary wall, they tend to stick. They have they are moving slower. If they stick to the top, they are moving much faster, right? That is my guess. But my guess is it's also a reasonable guess, right? So this is going to tell you u doesn't depend on x, which is along the streamline. It doesn't accelerate, right? But u also depends on the location between the different location between the wall. They should have a different horizontal speed. Okay. Any questions? Any comment for this? Wait. So if you are okay with this, okay, let's say now we postulated solution. Okay, and then in this case, okay, let's check. Let's check with the continuity equation. By the way, let's make you know, I forgot to say one thing. Let's make assumption flow is inviscid. Okay, assume inviscid flow. Sorry, not incompressible. Inviscid it cannot be, right? Because we are talking about the viscous force. Assume incompressible. So when you have incompressible fluids, what is the continuity equation? It's one of the under this incompressible fluid assumption. continuity equation is reduced to the super simple structure. 0 equals to nabla dot b. Okay, and then this one equals to du dx plus dv dy plus dw dz. Okay, so in fact, you know, if you plug in, right, what you want to plug in here is the let's say left hand side of the continuity equation is the, okay, this is the d dx of the uy plus dv dy, which is the d0 dy plus d0 dz. Okay. It's okay, right? I just plugged in this assumption. U is uy, v is 0, and w is 0. We plugged into this continuity equation to check if this assumption satisfies this equation. Okay, and then left hand side of the this equation is the like this, right? Second and the third term is the identically equal to 0 because, you know, you are taking the derivative of 0. And then first term is the you are taking the derivative of the function that only depends on y with respect to x. So what do you expect to the first term to be? If you take any function, if you take a derivative of the function, this, you know, you take a derivative of this u function u, right? And then if this u doesn't depend on x, if you take a derivative of this function with respect to x, this must be equal to 0, right? So it's simply, you know, it doesn't depend on that, right? So this one equals to 0. Okay, the comment here is the u does not depend on x, so dx of u equals to 0. This is the sum of the condition, right? So in fact, you know, so this is good. Our assumption, this is saying our postulated solution satisfies the continuity equation, right? So okay. So at least, you know, we are not, you know, our assumption, our postulate is not too ridiculous, right? Maybe, you know, if this solution doesn't satisfy this equation, this immediately tells, okay, your original thought is ridiculous. So don't even go ahead. Okay, but at this point, okay, at least we are qualified to solve equation further. Any questions here? This is the second step to check your postulated equation with the postulated set of solution with the continuity equation. Well, let's carry on. Number 3 is the, what was number 3? Okay, the simplify the Navier Stokes equation. Okay, number 3. Okay, so in this case, okay, let me try to just write. Okay, I'm going to write this. This is for the first time, so the let me just low gx. It's a bit tedious, but let me just do this. Y square d. Okay, this is u plus d square dz square of u ABC of the AU, okay? Then rho GY, EPDY, d square, dx square, I think, I mean, if you are using the iPad or something, just copy and paste and get ready for the discussion. This is so tedious. I should have made a copy, but yeah, this was my bad. Yeah. In fact, I really trying to make a copy earlier today, but my printer was somehow didn't work today. So those crap happens. But it's okay. E dx e plus v d dy v plus w d z of dv. Okay. Lastly, gz minus dpdz plus mu d square dx square w plus d square dy square w. Okay, almost there. W. Alright, I come here. Okay. So this is a set of the Navier-Stokes equation. Okay. This is the set of Navier-Stokes equation, and then now the postulated solution. Is the u equals to u of the y, v equals to 0, and then w equals to 0. Okay, u equals to u of the y, v equals to 0, w equals to 0. And then this is a fun time. You are going to start cleaning up all the crap here, right? All the garbage. Okay, so let's do that. Okay, the easiest thing is when you have a 0, right? Yeah, when you have a something equal to 0, which is y or u, v, w. v and w are 0, right? So let's try to clean up everything that involves v. Okay, first, okay? So v is usually associated with the y, right? So okay, so you can say dv dt is 0. This is 0, okay? This is also 0, 0, 0, okay? This left-hand side here is 0. Okay, let's look at the right-hand side. Same thing, b equal to 0. So this is 0. This is also 0. This one is also 0. It's not bad. Okay, this is good. Let's do the same thing for w. This w is equal to 0. So this one is 0, 0, 0, 0. Everything on the right-hand side is 0. Left-hand side, this is also this guy is 0, this guy is 0, this guy is 0. For all the viscous term, it's 0. Okay? And then what else? That's those, right? Okay? And then what else? Let's look at the u. Okay? Let's look at the u here. U depends only on y. Okay? U only depends on y. So let's say du dz, they should be 0, right? It depends on it doesn't depend on z. Same thing, du dx is 0. Okay? For this term, this is a v du dy. In theory, du dy can be non-zero. However, since v, it's multiplied with v, v is 0. Okay? So this one is 0. So this guy is also 0. Lastly, du dt, does u depends on t, time, right? So then du dt is also 0. Okay, so this, with this postulated solution, entire right-hand side is 0. Okay, what about this viscous term? d square u dx square. Does u depends on x? No, right? So then this one is going to be 0. Du dy. Okay, d square u dy square. This term, in theory, this might be non-zero. because we said u can depends on y, right?
Yes.
So this term is surviving. Okay, it's not bad. Du dy. The lastly d square u dz square. This one is also 0 because u doesn't depend on z. Okay. So we cleaned up a lot of terms, right? So indeed, this is not bad. Okay. So what else?
The G.
Yeah. Okay. Let's look at the g. Okay. In this case, gx, gy, and then gz, right? Okay. In this case, okay, what is the if we just follow the particular set of this flow, right? What is the direction of the g? This is the if I bring the drawing. If I bring the drawing here, okay. So in this case, right, this is between the wall, right? So we should have this is the direction of the g. Okay. This is the direction of the g should go downward. So in this case, gx equals to 0. Gy is going to be minus g. It's a negative y direction. And then gz equals to 0. Okay, so this is going to tell you this one gx is 0, gz is 0, this gy is minus g. Okay, okay, so that's last thing. Okay, so that's all. At this point, we don't know anything about the pressure. Okay, so we just leave the pressure here. So this argument makes the equation a lot simpler. Okay, which is going to be first term is going to be minus dp dx. Yeah, okay, yeah, we can go up. Yeah, minus dp dx plus mu d square u dy square equals to 0. And then second term is the, okay, let's say potentially this is the, okay, this is going to be a minus rho g minus dp dy plus no viscous term equals to 0. For the last one, for the z coordinate, it's going to be a minus dp dz simply equals to 0. Okay, so we have 3 equations. Any questions for this? Okay, so that's now we have a x, y, z. Okay, so we are making now we can do the solving. We can do the solving differential equation. But let me also make the notes. Okay, the pressure gradient. Okay, so this part was a little bit was not obvious, but when you apply the pressure right along between the wall, right, usually we say there is some pressure. Okay. So in this case, we can say, usually if we want to deliver the fluid by pressure, we say we put the pressure. And in this case, the situation is we are simply pulling the wall, right? So in fact, there is no pressure gradient in the x direction. Okay, so okay, so this means the dp dx, the pressure doesn't depend on x. So dp dx should be 0. This one is the I should have said that a bit earlier because for the second example is the so-called pressure-driven flow. Okay, second example is so-called pressure-driven flow, and then for that case, dp dx is some finite number. But in this particular case, since the fluid is purely driven by the wall, we can say dp dx is equal to 0. Okay. However, in the same way, let's say this is equation 1, equation 2, and equation 3, right? And this consideration gives you equation 1 is going to be it's purely mu of the e square u ey square equals to 0. Okay, this is going to be the one of the consequences here. The equation number 2, we are not, this is actually interesting thing. In this case, we have equation number 2 is giving you is the minus rho g minus dp dy equals to 0, and then this is going to be dp dy should be equals to minus rho g. Okay, that is the one of the equation we are getting. And then lastly, number 3 is also telling this is the minus dp dz equals to 0. So in this particular case, right, the interpretation of number 3, equation number 3, is going to be it's the p does not depend on z, right? Okay, p does not depend on z. Yes. Yep. P does not depend on the vertical location z. Okay, so this is actually telling you this is the so now we can say potentially p, right? P can be a function of the p of the x, y, z, t. Okay, this is the this is in general. Okay. However, p by the setup of the question, p does not depend on x. Okay, so we don't have this x, right? P does not by the this is a setup of the question. By the setup of the question, we say p doesn't depend on x, and then from the equation number 3, we can say p does not depend on z. Okay. And then in addition, we can say the p should not also depend on time, because after after pulling under certain stage we should achieve the steady flow. Okay, so this is the it doesn't depend on z either. Okay, so this is going to give you p equals to p only depends on y. This is one of the conclusion we can draw. Okay, so from here, right? Okay. This is the 2 prime. 2 prime is going to be in fact since p is the only function, only variable for p is a y. Okay, so dp dy is equals to dp dy. Okay, and then this one equals to minus rho g. Okay, so now we can find the pressure value. So the pressure you can solve this. This is a very simple differential equation. P equals to minus rho gy plus some constant. Okay, so this is going to tell you the variation of pressure between the walls. Okay. So at this point, without the further information, we cannot find the value for C. But we can actually say this pressure between the wall is going to linearly dependent on the y. Okay. This is one of the consequences for the by solving the Navier-Stokes equation. Any questions for this? Right. So that is the about the pressure. Okay. Let's say let me just say this one is the first one. Okay. First one is the pressure gradient. And then second one is the flow, okay, which is velocity. And then for this one, right, now you can solve this by the equation 2. Equation 1. Equation number 1 is giving you, this one is the mu of the du d square u dy square equals to 0. Right? This was the one of the differential equation that we had. And then in this case, since u is uy, okay, this argument is again the same. If the only variable of u is the y, right, this partial derivative can be considered as the regular derivative, right? So in this case, the du dy equals to du dy. Okay, so this is basically telling you, this equation is telling you, this equation is the d square u dy square equals to 0. Okay, now you can differentiate twice to find the expression for u. Okay. Integrate twice. Okay, which gives you one-time integration gives you du dy equals to some constant, let's say some constant c1, and then if you integrate second time, you should get c1 y plus c2. Okay, so the after this is after integrating this twice. Any questions for this? Okay, if this is okay, then let's try to go for the finding the. We also talk about the number 4 is the finding boundary condition. Okay, in this case, okay, finding boundary condition. We had the 2 boundary condition in this case. So let's say this guy is going to be u, and then moving at the u, right? So we never said, okay, let's follow the notation. The distance between the wall is, let's call distance is b, right? So in this case, let's say in the way we set the coordinate, at this point, at the bottom wall, we set y equals to 0, right? And then at the top wall, if the distance between the wall is b, at the top wall coordinate of the y is going to be b, right? So from here, can you please help me with the boundary conditions? The boundary conditions, so we know the, yes. Yeah, okay, u of the y equal to 0 equals to 0. And then u of the y equals to top wall, b equals to big U, capital U. Yeah, that's great. That's great. And then in fact you have a 2 boundary condition, and then 2 unknowns, which is C1 and C2. Okay, so let's call this is the okay. I just randomly use this is the again star star star. Okay, so the that's I should have said this solving this is a bit earlier, but okay, solve differential equation. Okay, in this case, okay, u equals to c1 plus c2, right? Yes, and then in this case, okay, we have a 2 boundary condition. So this is going to tell you, okay, the 2 boundary conditions. Is giving you, okay, the top one is going to be the first one, capital U equals to C1 times B plus C2. The second one is going to be, okay, y equals to 0. So and then 0, right? So 0 equals to C1 times 0 plus C2. Okay, and then this is giving you C2 equals to 0 from the second equation. And then C1 is equals to capital U over V. Oh, that's good. And I was not lying. In fact, the overall, what you get here is the U equals to C1. Since C1 equals to U over V, you are getting here U over V times Y. Okay. Wow! Congratulations. Now in fact, we have just solved this. This is the linear velocity gradient. With respect to y, with respect to y. Okay. So this is the interesting, right? This is interesting. And then also you may notice, right? Okay, tau. If you remember, tau equals to du dy, right? Since we can have tau equals to du dy, and then this can be found out mu times, in this case du dy is simply, if you take a derivative of u with respect to y, what you have left here is the mu times capital U over V. Okay, this is something that looks familiar. Okay, so that's sort of it's a long way, right? What I just did is I have found a velocity field. Okay, so and then actually overall I said U equals to this, right, linear, and then actually to be perfect or to be very specific, right, we also should have the two other conditions, which is the V equals to W equals to 0. We also have to say that if you want to show the perfect solution for the Navier-Stokes equation. Right. So in fact, right, this argument, telling you, okay, this is that's a good time here. So if you remember how we started the argument, okay. So here earlier, right? Okay, when I talk about what is Navier-Stokes equation, Navier-Stokes equation is the 4 equation and then 4 parameters, which is the U, V, W, and the pressure. Right? All of this should be solved by this equation. Okay, again the U, V, W, and the pressure, all of this should be solved by the Navier-Stokes equation. And then, in fact, what we did here is it's a bit long way, but by making the assumption and then trying to solve each equation, right? This is giving you, first we find the pressure gradient, the P equals to Py, and then this is some expression for the P pressure, how pressure varies within this between the pipe. I mean, this is nothing but, by the way, this is nothing but the hydrostatic, right? This one is the, by the way, this one is equals to, notice this one is gamma y, right? The same as hydrostatic. Okay, that is one of the solution. The second solution is about the velocity. 2 of the velocity is given as 0 by assumption, and then last velocity is found to be linear, so that we know as expected. Okay. So that is really the how we solve this. Okay. Was it quite long, right? But they be used to this. We are going to go through a few more examples here. But hope if you do more, I think you learn more. So let's try doing that. Okay. Lastly, okay. This is this is just one simple comment. But if you really want to play with the fluid flow in your life, try to get the big book. And then trying to sort of the shared book, and then you're gonna see maybe you can also do it with the card playing the card, right? When you have a card, if you put the share, you are going to see the the flow. The top part is going to slide more. Bottom part is doesn't slide at all, right? And then you can see actually the gradient of the speed. Okay, so that is just the one of the analogy to visualize a credit flow. Okay. Anyway, yeah, thank you very much for your attention for today. So let's come back to from the Poise flow from